Model and preliminaries. We assume an adversarial online model where there are n available actions x equals to 1, 2, 3 until n. At each time step t, an online algorithm H selects a distribution p to the t over the n actions. After that, the adversary selects a loss vector L to the t in the closed interval 0, 1 to the n, where Li to the t is in the closed interval between 0 and 1, is the loss of the ith action at time t. In the full information model, the online algorithm H receives the loss vector L to the t and experiences a loss LH to the t equals to the summations of pi to the t times Li to the t, summing for all those I starting from 1 to n. This can be viewed as an expected loss when the online algorithm selects action I in X with probability pi to the t. In the partial information model, the online algorithm receives L k to the t to the t, k to the t, where k to the t is distributed according to p to the t, and the LH to the t equals to L k to the t is its loss. The loss of the ith action during the first t time steps is Li to the t equals to the summations of Li to the t, summing for all those t starting from 1 to capital T, and the loss of h is Lh to the t equals to the summations of Lh to the t, summing starting from t equals to 1 to capital T. The end of the external regret setting is to design an online algorithm that will be able to approach the performances of the best algorithm from a given class of algorithms G, namely to have a loss close to Lg mean to the t equals to the minima of Lg to the t chosen between all those little g in capital G. Formally, we would like to minimize the external regret Rg equals to Lh to the t minus Lg to the t mean, and G is called the comparison class. The most studied comparison class G is the one that consists of all the single actions, i.e. G equals to X. In this chapter, we concentrate on this important comparison class. Namely, we want the online algorithm's loss to be close to L mean to the t, which is defined as the minima of Li to the t, where the minima is chosen between all I, and let the external regret to be R equals to Lh to the t minus L mean to the t. External regret uses a fixed comparison class G, but one can also envision a comparison class that depends on the online algorithm's actions. We can consider modification. Rules that modify the actions selected by the online algorithm, producing an alternative strategy which we will want to compete against. A modification rule F has as input the history and the current action selected by the online procedure and outputs a possibly different action. We denote by f to the t the function f at time t, including any dependency of the history. Given a sequence of probability distributions p to the t used by an online algorithm H, and a modification rule F, we define a new sequence of probability distributions f to the t equals to f to the t of p to the t, where fi to the t equals to the summations of pj to the t, summing for all those j such that f to the t of j equals to I. The loss of the modified sequence is LHF, which is defined as the double summation with the outer summation summing for all t and inner summation summing for all I with the term fi to the t times li to the t. Note that at time t, the multiplication rule f shifts the probability that h assigned to action j to action f to the t of j. This implies that the multiplication rule f generates a different distribution as a function of the online algorithm's distribution p to the t. We will focus on the case of a finite set f of memory-less multiplication rules. They do not depend on history. Given a sequence of loss factors, the regret of an online algorithm h with respect to the multiplication rules f is Rf, which is equals to the maxima chosen between all those f in fancy f for the term LH to the t minus LHF to the t. Note that the external regret setting is equivalent to having a set f to the ex on n multiplication rules fi, where fi always outputs action I. For internal regret, the set f to the in consists of n times n minus 1 multiplication rules fij, where fij of i equals to j and fij of I prime equals to I prime, for I prime not equals to I. That is, the internal regret of h is the maxima chosen, the maxima of term LH to the t minus LHF to the t, where the maxima is taken between f in f to the in, which is equals to the maxima chosen between index ij in x with the set of term, the summations of pi to the t times li to the t minus lj to the t, summing for all those t starting from 1 to capital T. The more general class of memory-less multiplication rules is swap regret defined by the class f to the sw, which includes all n to the n functions, f which maps from 1 to 3 until n to 1 to 3 until n, where the function f swaps the current online action I with f of I, which can be the same or a different action. That is, the swap regret of h is the maxima of LH to the t minus LHF to the t, where the maxima is chosen from f in f to the sw, which is equals to the summation summing for those index I starting from 1 to n of the maxima term, where maxima is chosen between the j and x of the following subset, the summations of pi to the t times li to the t minus lj to the t summing for all those t starting from 1 to t. Note that since f to the ex, which is a subset or equals to f to the sw, and f to the in, which is also a subset or equals to f to the sw, both external and internal regret are upper bounded by swap regret. See also exercises 4.1 and 4.2.